Welcome to the normal distribution. Only the most important distribution in statistics. Run out of space. Normal distribution is important because there's just so many phenomena that could be modeled by the normal distribution. It's a continuous distribution, which means that the variable that we are sort of capturing in the normal distribution can take on values from negative infinity to positive infinity. In some cases, however, the negative values may not make sense, such as time, volume, weight, etc. But there is an infinite number of possible values, and so that's why we call it a continuous distribution. The normal distribution is a bell-shaped curve that we're pretty much all familiar with. It's unimodal. Oops, I didn't draw that in the center. But we have the mean and the standard deviation, which measures the spread. The reason why this distribution is so popular is because, as I mentioned, a lot of phenomena can be modeled using this shape. For example, let's look at salaries. If we're looking at salaries, we have a few people making a lot of money, a few people making very little money, although some people may argue with that. But the majority of us are somewhere in the middle. And so we get this sort of bell-shaped curve. Let's look at grades. If we look at, we have some very smart people, but a few who get very high marks. Then we get some people who fail, very low marks. And then we have an average somewhere in the middle where most of us fall. So as you could see, this actually gives us a very effective way of modeling several phenomena. Let's look at another one. We could say sales, monthly sales. We may have, if we have a fairly stable system over time, we may have a couple of periods, months, that have very, very high sales, maybe around Christmas and so on. Some periods, very, very low sales, but the majority of the sales fall somewhere in the middle here. So the normal distribution, as I mentioned to you, is extremely, extremely important. And so we have to study it in statistics. Because it's a continuous distribution and it's also a probability distribution, in other words, this shape right here has some sort of function associated with it. And that function, we usually refer to it as a density function. It will allow us to calculate probabilities. So for example, let's say if I use this line here as x1, x2, and I was interested in what's the probability of falling in that range. So the probability that the random variable x lies between x1 and x2. Well, how would I find that? I would find that by taking the area under the curve. That area under the curve would be calculated in this fashion. So that probability, let's just call it P for now. I'll just put P by just to denote that, would be the integral from x1 to x2, whatever that function is. So we get into something really fancy, which is really integral calculus. And if you remember your differential calculus, you probably don't want to get into integral calculus because it can be a little bit messier than differential calculus. So as a result, we need a nicer, simpler, easier way to calculate probabilities from the normal distribution. So how can we do that? Well, we can do that if we have some way of mapping the normal distribution to another distribution which we call a standard normal. So f of z. So the random variable here is x, random variable is z. This has a mean and standard deviation, which is the population or the original distribution. This also has a mean and standard deviation, but its mean is actually equal to 0 and the standard deviation is equal to 1. That's a unique distribution. Mean is 0, standard deviation is 1. And the area under this curve, the entire area, happens to be 1. So it means that anything that is a part of that distribution is less than 1. So if I wanted to know what's the probability of being between x1 and x2, then what I needed to do is to figure out, let's just take that same shape, map it over to the standard normal. So this is our normal. This is our standard normal. And map it over. And then if we could figure out what this shape is equal to, this shape right here, then we have the probability of being between x1 and x2. So let's just, since we're mapping, we'll refer to this here as z1 and z2. So the idea is that the probability of x being between x1 and x2 is equivalent to saying the probability of being between z1 and z2. All right, so these things are equivalent. So since they're equivalent, what can we do? Well, let's see what we know about the standard normal. One of the nice things that we have is that every x value can be converted to an equivalent z value. Well, how do we do that? There's a relationship between these two curves, and it's as follows. So if we know the original x value and the mean and standard deviation of that distribution, we could calculate z, which we refer to as a standard normal value. Standard normal variate. So that's the z value. And so for any x, we could, as long as we have the mean and standard deviation of the population, we could convert to a z value. Question is, what do we do with the z value now that we have it? Well, let's figure this out. Okay. So in our books, we have a table. The table 0, 1, 1.0, 2.0. We have z values, and then we have a first decimal place in the first column, second decimal place in the second column, 0.01, 0.2, 0.9. And the idea is that if we can provide the z value, our table will tell us what this shaded region is. So provide the z value, and our table will tell that to us. So what we would do is, once we figure out the z value, we would look it up in the table, and we would get this area right here. The value that we get here is the area that corresponds to the z value. We'll call it AZ. So once we understand that, I think we're good to go. Okay? Let's try an example. So here we go. Let's just see if we had a simple example. What if monthly sales for a company average $15,000, right? With a standard deviation of $5,000. So we want to know, what is the probability that we get a period, a randomly selected period, with sales of $20,000 or more? What's that? So we would draw that 20,000 is larger than the 15,000, so therefore it should be beyond the 15,000. And since we want 20,000 or more, this is the area that we're looking for. All right? So how can we get this? Well, remember I mentioned that every normal distribution has an equivalent standard normal distribution. So if we take the standard normal and we drew it, then that standard normal Z would look something like this. Of course, my shapes aren't exactly identical. And the X value, which is the 20,000, can be converted to the Z value. So let's figure out what the Z value is. So it's X, which is the 20,000 in this case, the mean of the standard of the normal, 15,000, over the standard deviation, which is 5,000. So that is 20,000 minus 15,000. Oops, I got too many zeros here. And divided by 5,000. Well, that answer is 1.0. So what we now need to do is to take that Z value and look up the table. So if we look up the table now, Z 1.0, 0, 0, 0, 9, etc., we could figure out what the area is at that point. So what is that area? So it turns out that when Z is equal to 1.0, the area associated with 1.0 is 0.3413. So if we were to draw that, what we're saying is that when Z is 1.0, the shaded region is 0.3413. But that's not the area that we're interested in. If you look at our diagram again, the area that we're interested in is the area in the tail. But we know that because the standard normal is symmetrical and the entire area is 1.0, so therefore beyond the center line is 50% of that curve. In other words, the area is 0.5. So if I know this entire area here would be 0.5. So if I know this piece right here, I could figure out what the tail is right here. So the tail in this case would be, so here we go. Let me just minimize this. So the area in the tail would be as follows. Area associated with Z is equal to 0.3413, and so the probability of X greater than or equal to 20,000 is the same as the probability of Z being greater than or equal to 1.0, which is 0.5 minus 0.3413, which gives us an answer of 0.1587. So the answer to our question is 15.87%. Another space here. So our answer is 15.87%. There we go. And that completes this question.